Hi, welcome back to General Chemistry 1. Let's talk about significant figures and uncertainty in this video. First, we need to know how to count significant figures. When we count significant figures, we need to start to count from the first non-zero digit to the last digit. And if we have zeros as trailing zeros, they only count when there is a decimal. And if we have a scientific notation or exponential notation, only consider the first part of the number. Let's take a look at a few examples. How many significant figures are there in the following numbers? 32.3 degrees Celsius. There are three significant figures. We start to count from the first non-zero digit, 3, and 3, 2, 3. There are three figures, three significant figures. 320 Kelvin. We also start from the first non-zero digit, 3, and then 3, 2. The last digit is 0. It's a trailing 0, and this value does not have a decimal. So we don't count the trailing 0 without the decimal. In total, this number has two significant figures. 1400 meter. Starting from the first non-zero digit, 1, 2, 3, 4. In total, we have 4 digits. Because there is a decimal, we count the last 2 digits as significant figures. So in total, this number has 4 sig figures. 0.58 gram. The first digit does not count because it's a 0. We start with the first non-zero digit. So start from 5 and then 8. In total, it has 2 significant figures. 0.630. Start with the first non-zero digit, 6, 3, and then because we have a decimal, the trailing 0 count. In total, we have 3 significant figures. 6.7 times 10 to the 8th kilogram. It's a scientific notation, so we only count the first part, starting with the first non-zero digit, 6, and then 7. In total, we have 2 significant figures. All right, so now you know how to count significant figures, but why do we care about it? So that's something related to the uncertainty in measurement. For example, here we have a pen. We want to measure the length of the pen. We put the pen, we use a ruler to do that, and the resolution of this ruler is 0.1 centimeter. As you can see, the major tick has 1 centimeter in the length, and it's divided into 10 different smaller minor ticks. So each minor tick has a length of 0.1 centimeter, and that's the smallest accurate value you can read from this ruler. Okay, we put the pen against the ruler. The left is aligned with 0, and the right we can read from how long the pen is from the right. Get a zoom in picture. So you see the length of this pen sits in between 14 and 1 grid after 14, that's 14.1 centimeter, right? But you can obviously see it's, sits in between, but a little bit to the right. So we can estimate what's the portion of this length within the smallest resolution. So for this number, the length of this pen, we can say it's 14.08. It's between 14.0 and 14.1. The last digit, 0.08, the last digit 8, is an estimation. And it's the best estimation you can make. Okay, so the last digit is estimation. So it's an uncertain digit because we're not sure. Could it be 14.07? Yes, very possibly. It's an estimation. The uncertainty the uncertain last digit reflects the value that is smaller than the resolution of a meter. When you do any other kind of measurement, typically we treat the last digit as an estimation, a digit with uncertainty. Okay, so now we know when you have a measurement, it cannot be 100% accurate. You have uncertainty associated with it. So if we have two measured values, how are we going to do some basic math with it? How do we keep the minimum error or the most accurate results when we do the math? So first, let's talk about addition and subtraction. If we have two measured numbers and we're going to do addition and subtraction, we have to keep the fewest number of digits after decimal. Here is an example. 33.5 plus 23.28. You add them up, the results without rounds off, without any treatment is 106.78. The first number has one digit after decimal, the second number has two digits after decimal. So overall, the answer, we keep the fewest number of digits after decimal. So it's 106.8. In this case of addition and subtraction, do we care about how many significant figures are there? We don't. We only care about the digits after decimal. And here's an example of telling you why. For example, if a human weighs 62 kilograms, an ant weighs 1.01 times 10 to the minus 6 kilogram, what's the total weight of the two? It's an addition question. So we use 62 plus 0.000000101. We write the decimal format of the scientific notation. Add them up, it's 62.000000101, right? Because we need to keep the fewest number of digits after decimal, the final answer is 62. We round the final answer off to 62. What does it mean? It means the smallest weight, an ant, does not contribute. We can ignore that weight when we add these two things up because it could be very well buried in the arrows of the 62 kilograms. So for these addition, the bigger uncertainty dominates the results. The bigger uncertainty from 62 dominates the results. And we can refer the uncertainty from the digits after decimal. However, if we do the multiplication and division, we need to think about the question in another way. For this, we need to keep the fewest number of significant figures. So it's different than previous. For example, if we want to calculate an area, we use 9.2 centimeter times 0.3744 centimeters. These two numbers have the number of significant figures of 2 and 4 respectively. The final answer is this number, 3.44448. Okay, because we need to keep the smallest number of significant figures, we need to round the final answer off to 3.4 cubic centimeters with two significant figures. In this case, do we care about digits after decimal? No, we don't care about that. And here's why. For example, a pound of apple gets $0.05 more expensive in this month. How much more does it cost to buy 132 pounds of apple this month? So obviously you need to use $0.05 each pound times 132 pounds in total. So you get a number of $6.6. According to the rules, we need to keep the fewest number of significant figures. So 0.05 has one significant figures, 132 has 3, So for the final answer, we need to keep one significant figures, round it off to be 7. So in this case, we don't keep 3 because the small uncertainty from 0.05, one significant figures, they accumulate. So we don't keep more significant figures from in this case. Okay, so please remember different rules for subtraction, addition, multiplication, and division. Okay. In both cases, we need to round off the final answer to keep either the smallest number of digits after decimal or the smallest number of significant figures. But how to get rid of extra digits and round off for the final answer? Let's take a look at the rules for rounding off numbers. For example, here we want to keep one digit after decimal. We start with the number 0.21. We need to decide the digit value of the digits removed. If we want to keep one digit after decimal, we look at the second digit after decimal. In this case, this is 1. 1 is less than 5, so we dump the digit and round 0.21 to 0.2. Say, if we want to keep one significant figure for the number 21, we also look at the second significant figure here is 1 less than 0. We can make that digit as 0. So we can round 21 to 20. Please pay attention here. We don't want to add a decimal here. If we have a decimal, then the 20 point, that means there are 2 significant figures. All right, if we have a number that with the value of digits removed higher than 5 or more than 5, in this case 5.37, the 7 is more than 5, then we increase the preceding number by 1. We round off 5.37 to 5.4. Now we talk about 2 scenarios where the value of digits removed is less than or more than 5. How about the digit is right 5? Here we have a number 0.2501. If we want to keep one digit after decimal, we look at the second digit after decimal. This is 5. However, after 5, we have a few other digits. Now, this number is 0.2501. After 5, there are non-trailing zeros. Sorry, there are non-zero trailing digits. So in this case, we follow the rules of more than 5. So we round 0.2501 to 0.3. If we have a number of 0.25, the value of digits removed is 5, exact 5, no non-zero trailing digits. Then we look at the preceding digit. If the digit is even, in this case, 2 is an even number, then we can dump the digit or make that digit 0. So for 0.25, we run that to 0.2. If it's 25, we will run that as 20. The number 0.25, we don't have any trailing digits after 5. And of course, if we have 0.2500, the trailing digits are all 0. So it follows the same rule as 0.25, and it will be rounded to 0.2 again. If we have a number and the value of digits removed is 5, and we look at the preceding digit, the value is an odd number, then we need to increase the preceding number by 1. So in this case, 0.35, we run it off to 0.4. There is a rhyme that helps you to remember all the rules. Above 5, give it a shove. Below 5, let it go. What if 5, make it even? And that above 5, including the value of digits removed, is 5 with non-zero trailing digits. Not all of the numbers have uncertainty with them. There are some numbers called exact numbers that does not have does not have any level of uncertainty. For example, we have some unit conversion factors, say there are 60 minutes in 1 hour, there are 1,000 grams in a kilogram. That 60 and 1,000 is an exact number. It does not have any level of uncertainty. 1 hour cannot have 59.9 minutes, cannot have 60.1 minutes. It has to be exact, it has to be 60 minutes there. Another case for exact number is the counting numbers. For example, I have 3 coins in my hand. That's the number 3 does not have any uncertainty with it. Also, if we say there are a dozen of eggs in this box, you counted it's 12 eggs, there's no more, no less. So the counting number are exact numbers. So here's the question. If I tell you 1 centimeter equals to 0.0328 foot, is this number 0.0328 an exact number? No, it's not exact number because this unit conversion factor, it's a runoff from 0.328084. So it has uncertainty with it and is not an exact number. Another question. Does exact number limit rules for arithmetic operations, for basic math calculations? No. So when we have these exact numbers, we don't count that in the rules we discussed before. So for example, if we use 151 divide 60, although 60 only has 1 significant figures, we don't care about that because that's the exact number. The final answer should have the same significant digits with the measured value. All right, that's the end of this video. See you next time.